Vertical turbine efficiency.
This course project explores power generation of wind turbines in an array configuration. This project is inspired by traffic turbines developed in Istanbul, which were placed along highways to generate power from the wicks created by passing cars. John DeBeery, a researcher at Caltech, conducted research on how the arrangement of vertical wind turbines can affect the amount of power generated. Specifically, he found that the flow accelerations from the upstream turbine visibly affected the flow field encountered by the downstream turbine. And by designing VAWT arrays using a turbine pair as a unit cell in the design, there's a potential for an average 14% increase in array performance. Betts's limit is a law stating that the theoretical maximum efficiency for a turbine is 59.3%. This number itself is impossible to reach in reality and is usually around 35 to 45%. This project will analyze how close different arrays of VAWTS can get to the Betts's limit.
Our assumptions for our calculations are as follows. There's uniform airflow coming from the hairdryers with an average velocity of 21 meters per second. The angle of attack on the blades for the force calculations is 0 degrees, and the chord area is the swept area of the blade, which is 2,177 millimeters. Friction will be ignored. Our procedure for finding the power generated by each turbine is to use a velocity term from Bernoulli's equation to find the pressure caused by the hairdryers on each turbine blade. Using the force equals pressure times area equation, we can generate the force on the blade, which is plugged into the torque equation R cross F, where R equals 1.75 inches. The power is calculated by multiplying the torque by the angular velocity, which is found by counting the rotations in our experiment videos. The power for each turbine in the array will be normalized to get a single array power value. The efficiency of the turbine will be calculated using the theoretical power, which we will set to our calculated value. Now we have the coefficient of power, which by Betts's law cannot be over 59.26%. The two variables we need to find for our power calculations are the angular velocity, which we find through experimentation and counting the rotations, and the coefficients of lift and drag, which we find through CFD.
For our experimental procedure, we tested 4 different configurations, 1, 2, 3, and 4 co-rotating rows of 2 turbines as shown here. The number of rotations for each turbine was found by manually counting the turns in 3-second clips of the slow-mo videos. We normalized this data by dividing the total number of turbine rotations by the number of turbines in the array.
We ran a CFD simulation with air hitting the turbine in the z direction at 21 meters per second. The drag force is the resulting force going in the z direction, same as the wind, and the lift force is perpendicular to the drag force on the airfoil face, which means it's the x force. The calculations for lift and drag are their respective forces divided by the dynamic pressure multiplied by the frontal area of the turbine. The frontal area was calculated in SolidWorks, and the dynamic pressure was calculated using the wind speed and the air density at 90 degrees Fahrenheit, which is the temperature of the hairdryers. The resulting coefficients of lift and drag are respectively 0.000712 and 0.6712.
Here are our experimental results for the average rotations for each array. We can then plug these into our previously shown equations to calculate the coefficient of power for each of the arrays, which are shown in the slides. In conclusion, our experiment successfully showed that the coefficient of power generally increases with the array number, moving closer to Betts's limit using calculations of pressure and forces. Additionally, some future improvements include testing with more powerful and uniform air sources, increasing the size of our test array, and reducing the friction within our mounting structure.